two things. One is quantum error correction, other one is QAOA, right? Okay, so those two things we will discuss today. And quantum error correction would need some time, so I'll be concentrating more on that. Okay, and as time progress, we will see and we'll squeeze in QAOA into it. Okay, right? So as usual, let me start my right. Okay, I think you can see screen. Right. So yeah, quantum error correction. Okay. By the way, where do we need it is, as we know, we are in the noisy intermediate scaled quantum era, which means qubits, you name whichever way you realize qubits. Okay, qubits could be realized by artificial atoms. Okay, so which is transmons. Yesterday we had a brief discussion yesterday. So like IBM, okay, in India, QPI, okay, they are the ones who started coming up with quantum computers. Okay, right? So other one is photonic based photonic qubits. Okay, right? And something else, let's say NV center based diamond NV center based okay, NV center. NV means nitrogen vacancy in diamond. Okay, so you can realize qubits there also, right? And you can realize trapped ion, okay, and other things, etc. I will not name. If you take all these things, if you just see, okay, if you take all of them, they're supposed to behave as per our requirement. One is, if I just talk about a qubit, so the qubit means, mathematically I am going to represent on a paper like this. Okay, right? It's supposed to be in the ground state with some probability, in the excited state in some probability. Okay, where ground state is alpha square, excited state is beta square. Okay, that is what a qubit means on paper for me. In reality, qubit means it's supposed to be, let's say I'll realize a real world naturally occurring atom. So there is a ground state, there is an excited state, if you just take. Okay, and if you are realizing a qubit using an electron in the ground initially, if you put that initial electron in the ground to superposition state like above, so the electron should go up and come down, go up and come down. So it should be doing oscillations, Rabi oscillations between ground and excited. Just like if I just take a coin, if I toss a coin, it should be doing a flipping between head and tail, head and tail. When I try to catch it, it should fall to one of the state. Okay, right? So this is a qubit for us, but it has to oscillate with certain frequency. It will not oscillate because of the environment around. Okay, so the oscillation frequency, if you just take oscillation frequency, you plot in time, let's say oscillation frequency, it should be nicely doing, and after some time it deteriorate and then it fixed to one of the ground or excited state. Okay, so within some time it dies down, the oscillations would dies down. So that is a relaxation, that is called a T2 relaxation. Okay, fine. Now there is something called T1 relaxation also. T1 relaxation in the sense, let's say if the electron goes to the excited, Okay, it has to stay there for, let's say, some time, 1 microsecond, 10 to the power of minus 6 seconds. It is not staying there, it's that much time. It just decay back spontaneously or loses energy to the surround. Okay, that is a T1 relaxation. Okay, so it relaxes much before than what I intended, because to have oscillations like this, it is like the electron has to go up and stay there. By the time it comes down, okay, I will send another photon so that it goes up. Okay, so even before I am sending, it is dropped down, or it is mismatching for my next photon because it is not behaving as per my wish. So there is a relaxation on T1 also. Because of this, what happens? I intended to create a superposition like this. I would not be able to create a superposition like that. Okay, so that is a one of the error which is going to happen. Okay, and these errors may creep in maybe due to many things: environment, interaction with the surrounding qubits, or interacting with the walls. Okay, right? So because of these things, you intend to create a certain amount of data storage with some accuracy. You would lose that accuracy because of this errors. Okay, so there is something called environmental interactions would bring into something called decoher or decoherence. Okay, now we can understand decoherence instead of taking one single qubit. Let's say take a bunch of qubits together. Okay, when you take a bunch of qubits together, what happens? Okay, like what is happening with a single qubit? There are some qubits which are vulnerable to the surrounding, maybe the edge qubits, and they will decoher. Like the synchronicity, okay, or synchronization between all the qubits to behave in a one way is lost. It's like on a stage, if some 10 people are dancing in nice sync, we would see it's appearing or very appealing, very nice. Let's say one or two people are mismatching with other, it looks very odd. We'll say they are not in sync. So that is what happens when I take a bunch of qubits to do the computation. Among them, some of them are going out of the order. So that is called a decoherence. It's like the coherence word, which is actually associated with the lasers, where in the lasers, if you just take, okay, laser, if the light is coming, if the rays are there, if you just check any two rays, both are having same phase or fixed phase difference. That is what the laser. There is a coherence between the laser rays that will not exist in the case of the conventional light. So okay, so that is what the laser, the coherence. So such kind of a coherence is not there between qubits. Qubits are oscillating. It's like they're doing an oscillation like a waves. So those oscillations are becoming out of sync between each other because I'm take certain number of qubits to behave together in the same fashion, but they are not doing. So because of that, what happens? I will lose the context or the accuracy to store the information. Okay, so decoherence is a synchronicity problem among qubits, among considered qubits. That is one. T1, T2 we just saw. Okay, and there is one more thing. One more thing. Let's say there is a quantum state. I want to send through some gate U, and it's supposed to change it to some new quantum state psi prime. But the U which I am going to create, they have a malfunction in it. Okay, so that's a gate errors. Okay, so what happens? I intend to create psi prime, I created something else, psi double prime. Okay, so that is a problem for my calculation. Okay, right? That is also one error. Another error is there is something called crosstalk. The qubit 1, qubit 1, qubit 2, supposed to not to interact. They interact. Okay, or they may came with the vicinity, they interact. What happens? The crosstalk would lead to the errors. Lead to errors. Okay, right? So, and one more thing is, I get some psi out. I want to extract the information out. I'll make a measurement. Okay, but thing is, the way I'm making a measurement, I have some issues. My measurement toolkit has an issue, so which will lead to errors. Errors due to problem in measurement tools, measurement methods. Okay, right? So you can think in that way. Fine. Now I will write a little bit bigger. Okay, so that is one of the error, T1, T2 we just saw. And suppose I want to start the system in a particular ground state. Okay, initial state preparation. Okay, so what I intended, I want to start a 1 qubit in this, 2 qubit in this, okay, n qubit in this. Okay, but the problem is, because of the some problem in my preparation, I would end up in creating errors would lead preparation of something like 000, that is 1 and 0 n times. Okay, so your last but one qubit supposed to be 0, it is not in that 0, it is in a bit flip state, that is the error there. Okay, so this is the initialization errors. Okay, there is something called control line noise also come into the picture, fluctuation in the control signal. Suppose to create, okay, for example, from 0 I want to create a superposition state. Okay, what I do, I act a Hadamard gate usually. What it is a pi pulse, sorry, 5 by 2 pulse. So this pulse is submitted or created like given by a photon or some laser. So when I create that pulse, the control pulse, right, I might have some issue. So the state which is supposed to be equally superposition, it may not be equally superposition. It would be like the probability of 0 would be, let's say, 49. Probability of 1 is, let's say, 51%. Not equally. That would make some issue after some time. Okay, so there is a thermal noise also, like heat around the system also would create. So these are the various noises which are going to come in and create issues for our quantum computing. That's why, because of these issues, we say the existing qubits are actually noisy, and we are at the level of noisy intermediate scale quantum level. Okay, so one has to address this. Okay, either you come up with a new technology completely noise free, people are after it, or we can't wait for the technology to develop up to that point. Whatever we have, we should be able to do something out of it. So what we can do, we can come up with the error correction codes. Okay, right? So there are errors, I want to correct them. Okay, just like the way we are computing, we can come up with a code which corrects the errors which are coming in. Okay, so best way to understand this quantum error correction codes, quantum error correction codes, what we will do, we'll first try to see how errors are tackled or addressed in the classical computation. Okay, I would say first let's understand, okay, classical error correction methods or codes or whatever you want to say. Okay, right? So very good, I want to understand that. So what I'll do, let's just take some help from somebody who is doing classical error correction. Okay, how they do is they just follow a very simple technique. Let's say first they will find out if there is a bit 1 supposed to be 1 for some time, some longer time. You store information on some storage location to be 1, so it stays there in the form of 1. okay, with some probability, but it's just flips to a probable, like flips to 0 with say probability p. Very nice. And if it is flipping with probability p, which means it is not flipping with the probability 1 minus p. As we know, it is probability should sum to 1. Okay. Let's say I have a 0 in some other location. Okay. It remains to be 0 with a probability, some probability, and it flips to 1 again with a probability p. Just like other one bit is flipping the same way, 0 bit also flip. The flipping always the same, whether it is high to low or low to high. So I can say the probability of 0 to remain the same is 1 minus p. Okay, so this is how they just put the proper chances of a bit being flipped on the paper using this some kind of a diagram. Okay, so now this is there. This is just find out with what probability a system is flipping. Okay, now to after knowing how to tackle it, okay, that's the question. Suppose there is a location, so there is a location, there is a location, okay, where if I have 3 qubits in that location, okay, if I have a 3 qubits in this location, only one qubit flips. Okay, if that scenario is there, okay, what I will do in that case, I will take all those 3 qubits into a consideration. Now since we are talking in terms of classical, okay, let's understand classical. Now let's remove that qubitness there. Let's say we'll talk in terms of 3 bits, okay, not qubits. Okay, so there is a location where there is a 3 bits either in 1 or 0. For sure, we know that only one bit flips. Okay, so what I will call this all the 3 bits as logical 0, logical 1. Okay, right? What I mean is instead of carrying one bit information by one single bit, one information by single bit, I'll put 3 bits together and like 3 storage locations together to ensure that the same bit information is copied onto them. Okay, it is like cloning or copying or cloning or copying. Okay, right? So advantage with this is, as I took a situation where only one bit flips with what probability, with a pre greater than 0 flipping probability, sorry, not flipping probability, flipping probability, I'm sorry, you can take either way, so you should stick throughout the flipping probability. And remember, it only happens on one of the qubit. Such situation or such vicinity only I will take. So this is called binary symmetric channel. Okay, now what happens? Let's say if I store one bit of information on such location, as I know only one of them flips. Let's say first one flips. First one is 100. Okay, right? If you store in the first one 111, it flips to 1011. Okay, when I read, okay, reading this, what I understand, okay, what I understand is there are 2 bits which are in 0, there is 1 bit which is in 1, or I would say 2 bits are alike, the third bit is not in sync with them. So what I will conclude is there is a single bit flip. Okay, right? Because my situation was like scenario which I considered, only one bit flips. So a single bit has got flipped. Whatever remaining bits are there, those are the actual information carriers. So my information which I fed on the system, which is actually equal to 0, which is actually down bit. It's okay. So because of the error on the first, I would just disregard that and take the information from the remaining 2 bits. Okay, remember, same story would apply even for this 0 1 1. Okay, the 3 bits were like, one bit got cloned to 3 different bits or 3 storage locations. So one of them got flipped, the other 2 are remaining intact. So this says 0 1 1 is equivalent to 1. Okay, remember, this works only if single bit gets flipped. Okay, remember, only in that case. Let's say 2 bits gets flipped. If I get to know there is a location where 2 bits are getting flipped. Okay, we saw right earlier, there is a hidden bit string we can find out, right? Okay, right, using earlier algorithms which we saw. Okay, so likewise, I'll get to know how many bits are being flipped. From there, I'll come up with the alternate strategy to tackle that, or to ensure that the errors are not coming because of that kind of a flipping. Okay, right, this works only single bit flips. Now the question is, what if 2 bits flips? Okay, if I get to know that there is a location where 2 bits are flipping, right? We know how to find that. Okay, so we can figure it out. Fine. So the 2 bit flipping, what I'll do, I'll use the same technique. What I'll do, wherever I want to store 0 in that location, I'll copy that 0 into 5 individual bits and put the 5 bits there. If wherever I want to store 1 in that location, I'll take 1 and I copy that or clone that into 5 ones and store it. I'll call my initial one as a logical 0 and logical 1. Okay, now I know for sure 2 bits are flipping. Let's say among this, in that location, let's say 0 1 0 1 0, it happened. Okay, the bits are being flipped. Same story for the other one also. Okay, so now what I'll do, when I read, while reading, I read there are 3 bits are same, which is equal to 0 0. Other 2 bits are same, which is equal to 1. So now I'll follow this democracy kind of a strategy. Whichever one's having like same, maximum number of having the same, I treat it that is actual signal, which is 0. Okay, so same story here. There is 3 1s, so 3 are same, which is equal to 1. 2 are same, which is equal to 0. So altogether, I would say this is equal to 1. This is supposed to be 1 bit. Now again, this works only if 2 bits are only flipping, only if 2 bits flips. If 2 bits flipping, if more than 2 are flipping, then this doesn't work, because we might lose, we may end up in the wrong conclusion. Let's say 3 of them got flipped, 2 of them are intact. So I would think that, okay, the democracy, as per democracy, we have chosen a wrong leader, right? Okay, so that is what we need to know the strategy. Okay, so now, and one more problem, we can connect this to the probabilities also. Like there is a chances of probability having certain value. For example, okay, right? So there are 2 or more bit flips are flipping. Okay, 2 or more bit flips are flipping. In that case, the what we can do is you can find out what is the chances of such scenario? So you can use this probability and statistics. You can write two or more bits get flipped, get flipped. In that scenario, you can find out there is a 3p square 1 minus p. Remember, 1 minus p is what? Remaining intact, and p is corresponding to flipping. So out of 3 qubits, or 3 bits, 1 is remaining intact, 2 are flipping. In that case, what is the probability? So this is an expression which correspond to the probability of error occurring in the system beyond my control. My intention was to see only one bit flip, but it is going more than one. So the probability of error occurring, you can just do manipulation of this, sorry, doing some mathematical algebra, you can find out this is a 3p square minus 2pq. This is an expression, right? Now if you see, okay, if the probability of flipping, okay, that is p, if it is anything more than or anything close to half, then I am in trouble. Implies trouble. My error correction, logical error correction is not going to work. If p is less than half, okay, p is less than half, fine, fine. This will tell me the error is much smaller, okay, right? So how it is smaller? Because p of e is going to be remaining smaller than actual p whichever we are taking. So you can have a success in your correction code, right? This is important. So that's why to have the flip percentage should be less than 50%. If it is more than 50%, okay, so you have to have the, let's say there is two flips are happening. If p is more, okay, more than half, right? If two flips occur, then what you should do? You should take 2 plus 2 plus 2 extra bits you want to add, and then you have to take 5 bits storage for one bit store. Like what I'm taking is the logical 0 would be having 0005. It must have, okay, not 6, it's a 5. So that democracy would help us in this scenario, okay. So this is a simple technique you should always follow, right? So people used it classical computing, okay. So can we do that in classic quantum computing, quantum error correction? Okay, so can we create, the question is, can we create the same working principle here in quantum computing? Same logical, using a logical bits creation, okay. The question is, the straightaway question is no answer, but there is a catch. We could do something analog or similar to that, but we can do similar to that, okay, right? Always when there was one door shuts, the other door is there, we can do similar to that. By the way, why the question asks straight away answer no is, why no? Because cloning is not possible in the quantum computing, okay, or quantum hardware. You can't clone a qubit as it is. The other, earlier we are cloning 0 to multiple zeros, that is not there here. Okay, so suppose if I have a 0 cat, okay, I have to clone to multiple zeros. Of course it is possible, I'm just talking in terms of single bit, okay. But the question is, okay, this is possible, single bit cloning is possible, Okay, single bit cloning or just repetition. But what is not possible is, let's say I have a superposition state, the cloning into three superposition states is not possible. Okay, right? So what people thought, fine, I can't do that. Let's do something by taking some inspiration from classical error correction. What is that is, let's say, okay, quantum error correction strategy. Let me show you. Okay, what is that is, let's say I have a quantum state psi alpha 0 plus beta 1. Remember, here in this case, the errors induce, okay, what the error does, error induce 0 to 1, 1 to 0. Okay, so in that case, what happens? Okay, the errors would lead to like a bit flip error. You can say bit flip error. What it does, alpha 1 plus beta 0. Remember, probability amplitude got changed. When the probability amplitudes are same, not an issue. Equally probable situation. Okay. Hello. Okay, guys, can you hear me? Somebody was saying my voice is not audible. It's back now. Okay, okay. Yeah. So there's a power fluctuation. I think that's why maybe. Yes. Okay, there's a question. What is that question? Is there a written 5 zeros, sir? Is just an example or intentionally? Yeah, the 5 zeros earlier I wrote. Where is that? Here. Okay, instead of just storing 1 0, I'll store 5 zeros by copying. That is a classical scenario for you. Even though two of them got malfunctioning, other three guys are there to help me to find out what is actually stored in that location. That's was that. Okay, fine. Now, if the bit flip occurring in a cross quantum case, I have probabilities interchange. That is a very, very dangerous thing for us in quantum computing. So the probabilities must intact, remain intact. Okay. For that, let's say I have a quantum state psi. If there is a cloning possible, what I can do, then I can create multiple states. And let's say I know that there is a location where the quantum qubits, if I put, only one of the qubit gets flipped. Let's say there is an energy only to flip one of the bit. Once that bit, one of the qubit got flipped or changed its nature, the energy is over. There is other two bits are there, qubits are there. They may remain intact if that is the situation. Okay, remember, if that is the situation, in that case, what happens? I can see the other two guys are there, were intact, and I can find out that is the actual state. But the problem is cloning is absolutely not possible in quantum computing. So what I can do here, that was the classical computing people were doing. Here quantum computing people has to come up with a new technique that is called, okay, shifting the quantum qubit state to some other qubit state. Okay, instead of having a single bit qubit carrying the same information, they take three qubits together carrying the same information. Okay, that's the simplest way to explain. Let's say I have a qubit which is like alpha 0 plus beta 1. What I will do, I'll call the three qubits and take three qubits, ask them, please carry the information of three same information on your shoulders. Okay, so basically this is the basis on which it is constructed is 0 and 1, and same thing I take a quantum basis state, remember, it is 3 qubits, right? So I'll have 0, 0, 1, 0, 1, 0, 1, 0, 0, okay, 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay, this is the basis on which this is constructed, right? So this is the basis of 3 qubits, remember, and this is the basis of 1 qubit. Okay, so the same information, same alpha beta are put on the shoulders of 3 qubits. Now I am not doing put the information of psi on each qubit individually and ask them to travel. I'm not doing it because it is not possible to transfer same alpha beta onto 3 people simultaneously. It is not possible. That is actually a cloning. Cloning is not possible. So basically on paper, what I'm doing, I am doing a transformation from, let's say, let me call it, this is a single qubit basis state S1, this is S3. So transformation from S1 to S3 basis I'm doing. Okay, so that is a simple thing I'm doing. Okay, it is allowed, by the way, it is allowed in the quantum computing. Okay, so now what I'll do, I will call the 0, 0, 0 as logical 0, and I will call 1, 1, 1 as logical 1, which means what? My quantum state, which was earlier a simple quantum state like this, now I am calling it as logical quantum state, which is actually like this, okay, equal to alpha 0L plus beta 1L. Okay, if you just recall, that is what the classical people were doing. They take a 0 and put the same information onto multiple people. Here I am not doing it. I am take the same information, same single information, put on the 3 people. It is like if there is a large box is there, 3 people carrying front, back, and the middle. Let's say the middle guy just gives up, the last 2 guys are there to carry that box, or the one of the guy gives up, the other guy comes and relocate and ensure that box is carried without any problem. Okay, in the classical computing, what they were doing, so to send one box perfectly or without any issue, any errors, what they do, they create 3 boxes and put 3 on 3 people and send them off and tell them that you all 3 people carry, even though one guy just drops up in the middle, the box is gone, the remaining 2 people are there, they carry that information. So based on the remaining 2 people, we'll make out what is the actual information. Okay, right? Now both things work. Here also it works. Now the question is how we move from this quantum state to logical quantum state. Okay, right? So mathematically I just simply wrote basis change na. So quantum computing wise I should do that. Okay, how? As you guys know, it's all about quantum transformation, quantum unitary gates action. Okay, so I'll just show you a simple technique, a gate technique, where I just move from this state to this state. Okay, right? Fine. Okay, so let's say there is a quantum state, a quantum superposition state, which is, by the way, alpha 0 plus beta 1. Okay, beta 1. Okay. Okay, something is happening. One minute, huh? So I'm just doing the refreshing. It'll take few seconds. Yeah. Okay. Yeah. So, right, I'm writing 1. Yeah. This is a state I have. My target is to go from here to here. My target is to go from here to here. What I will do, I use the simple quantum gates of C naughts such a way, let's say there is one C naught here, there is another C naught here, okay, where the ancilla qubits which I am going to take both are zeros. Okay. Now, as you know, right, you can write down the layers. The initial quantum state is psi and 0 in tensor, which you can write down as alpha 0 0 plus beta 0. Sorry, there is one more, alpha 0 0, okay, and 1 0 0, beta 1 0 0. This is the state I have in the first case. Now there is a C naught gate after the first like from first gate, first qubit to second qubit. Now you see the psi 1 is a C naught between Q0 to Q1. Okay, right? So you can call the first one as Q0 and second one as Q1, third one as Q2. Okay, so if you do that, okay, so you can write the C naught between Q0 to Q1, okay, and Q last qubit goes as it is without being manipulated. So psi 1 would be, if you see, the first qubit is 0, so second nothing happens to the second qubit. Okay, third qubit intact. First qubit is high, second qubit must be flipped. So beta 110. Okay. Now I got what is the psi 1. Now I want to find psi 2. What is psi 2 by the way? Psi 2 is C naught acting between Q0 to Q3. Okay. Now you see Q1 in the Q1, Q0 is 0. So nothing should happen for Q3. But when the second case Q1, Q0 is 1. So the Q3 must be flipped. Okay, see, now I got what I'm actually intending in the first place. Okay, so this circuit of two C naughts put together between first to second and first to third would ensure that basis change. Okay, now I know if one of the qubit also get flipped, okay, the errors would lead, let's say psi 2 prime I am going to get, like one of the qubit, first qubit got flipped, okay, right, this is what I have. Now I just check on the other two guys where they are at, what is their probability amplitudes. Okay, other two guys, the ground state probability amplitude is alpha, excitation probability amplitude is beta. So I take that information to be granted as the right qubit, right information. Okay, so this is a technique used if this works, if the error is going to occur on only single qubit. Okay, now the question is, what if more qubits are going to be affected? Let's say two qubits are going to affected. In that case, we'll follow the same strategy. My 0L would be 0 0 0 0 0 if two qubits flips. Okay, now on the same way 1L would be 1 1 1 1 1, right, which means I need to upgrade the quantum circuit accordingly. So instead of having only two ancillary registers, I'll take two more ancillary registers where there is a psi. So there is a C naught, there is a C naught, there is a C naught, there is a C naught. Okay, so the output would be alpha 0 0 0 0 0 plus beta 1 1 1 1 1. Beautiful. This is how I will tackle all the errors would occur. Now, again, this has some drawback obviously because I have to increase the ancilla qubits as many as like I needed depending on the errors occurring in the system. Okay. Now that is a bit flip error for you. Now, let's say you figured it out. There is some error occurred. Okay, right? You figured out some error occurred. I want to put back that error back into the same form. Let's say I want to tackle, I want to address that error. I don't want any errors retaining, and I don't want just disregard some information because of the error. Okay, what is that is, let's get back to the 1 qubit scenario where this is the information which is converted into a logical quantum state as alpha 00 plus beta 111. Okay, beta 111, right? Okay. So okay, let me refresh. Cancel. Okay, just give me a second. Right. Okay. Beta 111. Okay. So if this is there, due to errors would induce this to become something like alpha 100 plus beta 011, which means error is at first qubit. Okay, fine. I want to put that qubit back into the play, right? I don't want to disregard that qubit. In quantum computing, we are dealing atom by atom, qubit by qubit. Okay, even one single qubit is a much valid thing. Okay, so now whether the first qubit got flipped or second qubit got flipped, third qubit got flipped, I want to do, right? So I have to do some kind of a diagnosis. Okay, some some way of finding where the issue is. Okay, so for that there is a technique, there is a tool I can find. The tool to find where is the error, or you can say where is the bit flip. Okay, where bit flip occurred. Interestingly, you can find or you can create a tool, okay, right, using the basis technique, basis elements. Okay, what is that? If you just take, okay, if you just take 000, this is one of the basis of 3 qubit system. See, you see all the qubits are alike. Okay, right? So when you send the information in this form, it remains the same throughout the output, means there is no error occurred. Okay, so let me create a matrix out of it, 000, by taking outer product of same thing. Similarly, if I have information sent like 111, it remains the same, it comes out as it is without being manipulated, I would call there is no error. So let me create a matrix out of it. Okay, now I sum them up and I'm calling is a projection operator, where if there is a quantum state is there, if you act a projection operator on the quantum state, okay, operating a projection operator on a quantum state, it's not just only p not acting on psi, you do take on the other side also. This is the a kind of a measurement technique. Okay, measurement. Now what happens if you just take psi, p not acting on psi, if you get 1 with this result, which implies no error. What I mean is the psi is only having, which implies only having base elements or the substates as 0, 0, 0, 1, 1, 1. That is what I meant. Okay, you can cross check if you want. Just take the P naught, act on psi. Our psi is what? Our psi is, let's say this is the psi L. Okay, so the P naught acting on psi L, if you want, you can give quality L, L, L. Okay, psi L, which is, okay, 0, 0, 0, 0, 0, 0, outer product 1, 1, 1, outer product 1, 1, 1. Okay, multiplied on to, okay, what is my quantum state? Quantum state is alpha 1, 0, 0, 0 plus beta 1, 1, 1. This is a quantum state. Now if you see, inner product between this and this is 0, inner product between this and this is 0, right? There's supposed to be 4 terms out of it, but only 2 terms would come. What are those terms, right? The terms which we are going to get is inner product between this and this is 1. So I would get alpha. Okay, if you want, I can just write down explicitly. Okay, so explicitly what I get, 0, 0, 0, alpha 0, 0, 0 plus 1, 1, 1, 1, 1, 1, beta 1, 1, 1. This is what the other 2 terms are getting 0. So you can take out the alpha out. You can take the alpha out. If you want, you can put it here. This is a constant you can put anywhere. So you would get the psi L itself. Okay, and now when I multiply P naught psi L on the left also psi L, what you get is psi L with the psi L, which is equal to 1. So what I mean is, when I act the projection operator P naught on psi L, if I get 1, which means there is an error, no error in the case, in the situation. Suppose if there is a 1 error occurring in the stream of qubits which were sent, let's say the first qubit got flipped. Similarly, if the stream is sent like this, first qubit got flipped. Let me construct a projection operator, a tool which tells me first qubit got flipped. How? Take them and create a projection out of it. Okay, right? Now let's say by any means, my quantum L state is, let's say the first qubit got flipped. Okay, first qubit got flipped. Let's say if first qubit got flipped, now you take a inner product action of P1 on psi L on the left and right. Now you see, right? Okay, the inner, like there is an inner product would exist between these two. Okay, right? So all other 2 terms are 0, so I'll get 1, which implies error first qubit flipped, or error is at that qubit. Okay, remember I'm talking specific scenario. Now P1 is the one, is the tool which tells me first qubit got flipped. Okay, tells me first qubit flipped. Okay, right? Similarly, I can construct second bit got flipped case. That would be, you can generalize. Okay, you can generalize plus 101. I'm sorry. Okay, let me write down neatly. 101 outer product. Okay, 101. Okay, so what I mean is, let me show you in my presentation. We'll take a break before, after that. Okay, okay, just a minute. Yeah, right, just a minute. Yeah, here if you see. So my P naught is all zeros or all ones, no error. My P1 is one of the first one is flipped. Okay. P2 is second bit got flipped, and P3 is the third bit got flipped. Okay. So by just acting P0, P1, P2, P3 on the quantum state, okay, right, on the quantum state, what happens? I would get a chance to find out whether the quantum state which I have chosen is got flipped on first or second or a third, or there is no flip at all. Okay. So just by knowing what happens, I can easily find out where the error is, where the problem is. Okay. So interestingly, let me give you one simple technique. Okay. One simple technique is, okay, similarly P2 and P3. P3 is, okay, let me finish it off. Then we'll take a break. 110, 110. Okay. Now, as we know, if P3 is giving me 1, which implies straight away you can imply only one qubit going to have an error in the system. In this case, P0, okay, P0 is 0, P1 and 2 all are zeros, okay, P1 is also 0, okay, right? So what I will do, you can see interestingly, if P3 is having an error means the third qubit got actually flipped. Okay, this is the scenario. Okay, wait a minute. This is a scenario, third bit got flipped. What I will do, as I know third bit got flipped, I'll send this information. Let me say this is psi prime by mistake. It's supposed to be psi, it become a psi prime. If I send that through, let's say a gate constructed out of identity, and a X gate. Okay. What I mean is, I'll take psi prime, send that through. Psi prime is a combination of 3 qubits. Send that through I tensor X. So what happens? X qubit, X gate acts on this last qubit and flips that to psi as it is. Okay, as we know, X flips 0 to 1, 1 to 0. Okay, so the question is, if I know P3 is giving non-zero, then only I can have a X gate in the third qubit. If P1 is non-zero, then X qubit was. If the average, okay, there is a psi here, there is a psi here. If this is P1 is 1, implies my correction gate is X tensor I. Okay, so this is the correction term which I am going to have in the circuit. So first you have to detect the error, and then correct. Correct is done by either sending the same information back through the same gates once again, or if you want, you can create a correction gates like what I was showing here. Okay, right? So we'll quickly take a break, and we'll continue from here, and we'll see some circuit for how the correction is done. Okay. Okay, T1, T2 people are asking from T1 is about a